So in this video, what I'd like to talk about is the angular dependence of the scattering intensity when we're measuring a polymer. So the key concepts that we need to remember for today, actually the main concept, is that polymers are self-similar. And we've said this a few times in the last couple of videos, and it's so important for understanding the scattering measurement. So when I say something like that, when I say that the polymers are self-similar, remember that what that means is that if I look at a polymer chain at a big length scale, I could characterize it by something like its end-to-end distance. We've been calling that R. Of course, it's a vector. I've left off the vector notation here. But there's more to it than that, because if a polymer chain is self-similar, then if I was to look at a smaller length scale, then I could characterize the size of this also, maybe by a smaller size. Let's call it lowercase r. And both capital R and lowercase r would depend in the same way on the number of monomers that are within these regions. For example, if I looked at the whole polymer chain, then that end-to-end distance, let's just say squared, would be equal to b squared times n to the 2 nu. Or we've also been saying a lot that r scales as n to the nu power. That's great. It works. We've done this to death, right? Whether we have excluded volume or not. If we look at the small region, then if something is self-similar, then it means that r squared will be equal to b squared times little n squared to the 2 nu, where little n is the number of monomers in that region that I've circled. Or of course, the other thing, r scales as little n to the nu power. So that's what I mean by that. Now, we've looked in a little bit more detail at this, because if I have a polymer chain, we've looked at the probability of having a polymer chain with n monomers and a size r. And what we saw is that is equal to this prefactor, 3 over 2 pi nb squared to the 3/2 power. That prefactor is just to normalize it so that the integral of the probability distribution is equal to 1. And then that is multiplied by the exponential of minus 3r squared over 2nb squared. And so if you think back to statistics or whatever, if you were to plot this function, then this function would look like a bell. So this function is a Gaussian function because it gives the Gaussian distribution. Okay, and that comes from the fact that this variable is squared up top. Okay, so let's clear that out. Clear. Okay. So if a polymer chain is self-similar, then that also means that the probability of having n monomers that are a distance, let's say rjk apart, and you'll see where that rjk comes from in a second, then that would be equal to this thing here. So let's call this A. Actually, you know what? Let me be specific and put in what it would be. This would be equal to 3 over 2 pi little n b squared to the 3/2. And then that exponential term, we're just going to have to make the appropriate substitution. So this will be equal to, or this will include the exponential of minus 3rjk squared over 2nb squared. Okay, so that's what self-similar means. And remember that these, well, self-similarity is what links these two things together, and that they are both going to give you Gaussians. So we get a Gaussian chain. So if we just look at the second expression for the smaller region inside of the polymer chain, what does this mean? It means that if I look at the polymer chain, let me specify 2 monomers. So let's make, let's put this one here. This will be monomer J. And let's put the other one far away. Let's put the other one here. This is going to be monomer K. Then RJK is going to be the distance between these two monomers. So this was RJK as a vector. And there will be, if I was to count from J all the way up, chase this around, blah, 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 all the way to K, then there would be n monomers, little n monomers between monomers J and K. So that's what the probability distribution is telling you. So another way of doing this, if you look, b squared n, that's just, let me be explicit. B squared n is just going to be related to the square root of what I expect that to be with, or what I expect that value to be to begin with, right? If it's a random walk, then r will be b times the square root of n, or r squared will be b squared, or what am I doing? Get rid of that squared. It's 2nb. Right now it is squared. Sorry. Anyway, the point that I'm trying to make here, though, is that this exponential can be written in terms of a variable x. And it goes as the exponential of minus 1.5 x squared. That's why we say it's a Gaussian distribution. This is only true when the excluded volume is 0. If it's not 0, if we have, let's say that the excluded volume is greater than 0, then the probability, you can work this out. I'm not going to do it, but the probability distribution is going to be a little bit different, actually. It won't be Gaussian. And this will look like minus 1.2 times x to the 2.43 power. So keep that in mind. We're going to rely on the fact that this distribution is always going to be Gaussian, even when the excluded volume is not equal to 0. But just remember, if this ever comes up, that that probability distribution is not correct if the excluded volume effects are present. So what on earth does this have to do with scattering? Why am I reminding you of this? Well, let's go back to what the problem is that we're trying to solve. The problem that we're trying to solve here is that I've done a measurement of a polymer chain with small angle neutron scattering. I've gotten a curve out that looks like this. And now I need to interpret it. I need to figure out what's going on. Remember that, roughly speaking, this region is what we call the Guignay region. So I can make a Guignay plot and I can fit it. Remember that that will be linear and I can get the RG from that. So I can get RG. And remember also that in addition to getting RG like that, I can also fit using Guignay's law to get what the radius of gyration should be. Remember that down here, the intensity is constant. And that in this region, the intensity decays. So there's a power law where I of Q scales as Q to the minus D, where this, according to Perot's law, is the fractal dimension. If I put this on a double log scale, the slope here would be minus D. So I'll use those interchangeably. Sometimes I'll say that it's minus D here. I mean that if you were to put it on a double log scale, that would be the slope. The way I'm drawing it here, the data is already on a double log scale, so the slope is actually -2 the way that I've drawn it here. But in terms of the actual numerical values of the data, this is how it decays. Okay, so it'd be nice if we could explain that. It would be nice if we could explain why the intensity is constant here. We've already seen why the intensity falls off the way that it does here, although it would be interesting to see what it corresponds to physically. And what would be the most useful is if I could come up with a mathematical expression for this orange curve. And that's exactly what we're going to do in this video. So the starting point to do that is, what am I trying to do? I am trying to model the intensity of neutrons that I measure as a function of angle. And angle is contained in Q, so we're going to look at this as a function of Q. So this is proportional to that quantity we've looked at before, which is the form factor. And the form factor is just going to be the intensity at some angle Q relative to the initial intensity of the light. So this means that the form factor, P of Q, is always going to be between 0 and 1 in terms of the values that it takes. Now, it turns out that if you have a dilute solution, so just a few polymer chains in there, and I'll just say for the record, that's how we typically measure these things. We put in like, I don't know, 1 to 5 weight percent of polymer in the solution. Of course, that depends on the length of chains and things, but we're talking like 30 milligrams of sample per milliliter of solvent. So pretty dilute. When we do this, the intensity is going to be equal to the structure factor. Actually, I should say the intensity is going to be equal to the contrast. Remember, the contrast is how the different isotopes scatter with respect to one another. So it'll be equal to the contrast times the structure factor. And that will be the contrast times the degree of polymerization of my chain times the form factor. So you can see my goal here is really to figure out what is the form factor. And if I do that, then I understand how the scattering is going to work as a function of Q. So then I can fit it using least squares fitting and extract the values that I care about. Okay, well, let's try to get some of these limiting behaviors. Let's first remind ourselves what Q is. Remember that Q is in what we call reciprocal space. In other words, if I look at the units of Q, Q has units of inverse length, so inverse angstroms or inverse nanometers. Well, what are the units of length? Well, the opposite of that. So if I was to look at the size of my chain, the size of my chain would be in units of angstroms or nanometers. So if I look at the case, let's just look at the Guignay region first. So the Guignay region is right in here where I can see the size of my polymer chain. So in this case, when we did the expansion, we said that the Guignay region was given for Q times the radius of gyration less than 1, and that allowed us to do the Taylor series expansion. In other words, this is Q will be less than 1 over Rg. So the Guignay region is the region where we're looking at the entire particle. We're not looking at small length scales, we're looking at the entire particle. So that region here, this is Q, it's really about equal to 1 over Rg and then lower. That's the Guignay region. So we've done that, but let's look at the Perrault scaling. Let's look out here where we have the scaling or the decay of the intensity. Well, let's go to large values where, let's, for example, say, let me write down what we're doing. This is the Perrault region. And let's look here at the case where Q is much, much bigger than the size of the polymer chain. Remember, R and Rg are related by a numerical prefactor. So this is the same thing as saying Q is much, much bigger than 1 over R. What does that look like? Well, that looks like us looking only at a small region of the chain like that. So that's what we're doing. So what happens? Well, let's go back. The scattering the intensity that we see is going to be related to the structure factor. So what is the structure factor? Well, the structure factor we can define, and we kind of did this before, but this is 1 over n, summation j equals 1 to n, summation k equals 1 to n, of the average value of the exponential of minus I q dot r rj, the position of the jth monomer, minus rk, like that. Okay. So this r sub j minus r sub k, what is that? Well, that's how far they are apart. So this we can call rjk. That's how far the monomers are from each other. So the structure factor then is 1 over n, summation over all of the monomers and all of the monomers around that monomer, then times the average value of this function e to the minus I q dot r j k. So we can just calculate this, right? Well, sort of. If I'm doing a computer simulation, I know what r, j, and rk is because I know where the positions are for all the different monomers. But imagine that I'm making a sample and I've got billions or trillions or an Avogadro number of monomers in there. Well, I don't know where all of those are. And even if I did, it's not like I could use that because they're constantly moving. They're jiggling around and rotating and doing all this stuff. So that doesn't help me very much from an experimental standpoint. So I'd like to be able to figure this out somehow. Okay, so I've got to take that into account. And that's what we're going to do in a second. But let's go back and let's just focus on the Perot region. Let's not look at the exact mathematical details of this expression yet. Let's just see what we would expect to happen. Well, if I go out and look at a region like I've drawn in the circle here, then what I've got is a region like this. In fact, let me make it a little bit bigger. And inside, I've got some monomers. And then it goes off to the rest of the chain. So this region here, we will call, or it has a size of 1 over q. We could have called it r. This is the same thing as r. Okay, 1 over q. And it has a volume 1 over q cubed, or r cubed. And the last thing is that in this region, there's going to be a certain number of monomers. So in a region with size 1 over q, I have n sub q monomers. So that's all the information I have about this region. So again, like I said, we're going to look at the Perot region where q is much, much bigger than 1 over r. And what that means is that we're looking at tiny pieces of the polymer chain, but we don't see the whole polymer chain. So I can look at this expression for the structure factor, and it turns out that the function in the brackets, this thing, is going to be approximately 1 at these high values for reasons, okay? For reasons that I won't go through because this is not a scattering class. Well, if I look at that, if I have this sum, so again, let me just write it out. S of q in this region is going to be 1 over the number of particles that I have there, so 1 over n sub q, times the summation as j goes from 1 to whatever, and k goes from 1 to n of 1. Well, I've got a double sum, so this will give me the number of monomers in that region squared. So this will be n sub q squared divided by n sub q, or n sub q. You're like, so what? That's what you said there. That is what I said there. But what I can do is I can figure out how many monomers am I going to expect in that region. I can do that using the chain statistics that we've already seen. So what is n sub q? Well, I don't know, but I know this. I know that the size of this region, R, which is equal to 1 over Q, is going to be related to the number of monomers in that region. Let me see. It's going to be n sub Q in that region times what? Times the power nu, and then multiplied by the Kuhn length. Well, that's useful, huh? Let's just take this part here and work with it. Then this means that n sub q will be 1 over b times q, and then I have to take the root, right? Because this is raised to the nu power. So I take the root, I get 1 over nu. So n sub q is going to be b times q to the 1 over nu power. In fact, minus 1 over nu power because it was in the denominator. Does this look useful yet? Well, this is, remember, this is n sub q. This is also s of q. And that's related to my scattering intensity. Is this useful or is this not? Well, let's look. So here's my intensity, which is proportional to the structure factor. I'm looking at large values of Q, length scales that are smaller than the size of my polymer chain. So here's the stuff that I don't care about. And there's my scattering. Is this useful? Well, yeah, it says that right here, the scattering intensity, the structure factor, scales as Q to the 1 over nu. Well, let's just try a test case. If I have a polymer chain that's an ideal polymer chain, then nu is equal to 1/2. Well, if nu is equal to 1/2, S of Q scales as Q to the -2. That's cool. That's what we know happens. That's what Perot's law told us. So we got Perot's law out of this. So this is good. This is a check that everything that we've done so far is working out. And I say this because when you're doing research or when you're working on a product, you're developing a product, you have to check to make sure that you're on the right track, right? How do you self-consistently make sure that you're doing things right? Well, when you're taking a class, that's why there's answers in the back of the book. You can make sure that what you're doing is on the right track. When you're working in new areas, there is no back of the book to look at, right? So things like this are what are going to help us to make sure that what we're doing is actually describing what we're measuring. It's going to help us check to make sure we're getting the right scaling of everything. So that's good. I told you in a previous video, what do you expect if Perot's law is true? What do you expect the intensity to decay as if you have a polymer with excluded volume that's greater than 0? Well, you know that in that case, the excluded volume parameter, or the Flory exponent, I should say, is 3/5. And if you go through, I think I did this in the office hours video, if you do this, you would find that the intensity of the scattered radiation falls off as Q to the -5/3, or in other words, Q to the -1.67. Well, if you look at this, that looks like 1 over nu. So for a polymer, the fractal dimension is equal to 1 over nu. So what we did in coming up with this expression was we showed that S of Q is equal to Q times B to the minus D power. That's Perot's law. That's great. Okay, let's look at the final limit. How far can we go? Well, if Q is equal to 1 over B, then S of Q is equal to 1. Does it make sense to go smaller than the monomer size? No, there's nothing there. So in other words, S of Q is equal to QB to the minus D power for what? If 1 over B is less than Q is less than 1 over R. All right, so this is the region in which this is valid. And remember, for comparison, Guignet's region is when QR is less than 1. In other words, when Q is less than 1 over R. So we already know that this is valid for the Guignet region. Okay, this is the Perot region. All right. So hopefully everything's making sense. We're just taking these concepts that we described in a previous video and just adding some layers onto it, being a little bit more explicit about what we mean. All right, so what if Q was less than 1 over R? Like, can I get anything? Let's just say much. Do I want to say much less? Let's just say less than 1 over R. In addition to the Guignet stuff that we've talked about, is there something I can get in terms of the intensity of the scattered radiation? Well, let's do that. If I have a polymer chain, this is going to be its size. And in this region here, what do I want to say? How many monomers am I going to have as a function of Q? Well, NQ is going to saturate, not 1, no, my core. It's going to saturate to N. It's going to be the number of monomers in my polymer chain. Right? So S of Q, you would expect, would be N. All right. So what you see that this is constant. So that means that in terms of our graph, we've described this part where S of Q is constant. And again, Guignet's law is giving me this intermediate region here. I could do this another way. If I have this size of a polymer chain and I have N monomers inside, I could talk about the concentration of monomers that I have. So the concentration of monomers, we've done this already, is the number of monomers that I have divided by R cubed, which is the same thing as N times Q cubed. So if I want, I can also define this region instead of in terms of size, I can describe it in terms of concentration. So in this case, when Q is, let's see. Let me see. Okay. So this means that Q is equal to the concentration of monomers divided by N to the 1/3 power. So if, at this point, I guess. So what I can say is that if Q is greater than Cn divided by N to the 1/3, we see intrachain scattering. In other words, the intensity that I'm measuring experimentally is going to be due to correlations, the positions of the monomers with respect to each other inside of the chain. And if Q is less than this value, I'm going to see interchain scattering. At least when Q becomes small enough. So in terms of a physical picture, when this is true, when Q is less than this concentration divided by N, then here's one big polymer chain. And let me just duplicate it to show you what this looks like. So this other one's over here. Then if Q is less than this concentration, I see interchain scattering, then not only am I considering, or not only do I have this structure factor term that is equal to N due to just the polymer chains themselves, so scattering from just individual polymer chains, but I'm also going to have to start considering the effect of a monomer in one chain being correlated in terms of its position with a monomer in another chain. In general, this is a difficult problem to take care of. It's not something that we can do analytically. So, well, we can, but it's not something that we can always do analytically. We can't just generalize it. So in this case, this is why we focus on a dilute solution. Because these correlations are going to be so far apart from each other. These polymer chains are going to be so far apart, and the distances between them are going to be so big that this will not contribute. So in other words, in this region, S of Q will just equal N like we described above. And if Q is greater than this value, remember that means intrachain scattering, then S of Q will be N times P of Q. Or P of Q will be 1 over N times S of Q, and I gave you those expressions already. Okay, so this is just setting things up. We see that at least with this simple description, we're getting the right behavior. We're getting, I'll draw it one last time. We're getting the general shape of the scattering curve, right? In other words, when S of Q is equal to N, we have something that's constant. When we start to get to the region where, I should also say this is Q less than Cn over N to the 1/3. When we get above that, then the scattering intensity starts to decay away. And our check at the end of the day to make sure that the function that we come up with is correct is the slope of this line here should be minus d. So the limit as Q goes to infinity of our form factor had better look like the scaling that we know exists from Perot's law. So this should look like 1 over Q to the d, if we're correct. Okay, so that's the outline of what we're going to do. We already know what happens down here. Guignet's law tells us a little bit about what happens in this region. Perot's law tells us about the scaling of this curve. And now the next thing we're going to do is take this definition of the structure factor and of the form factor and get a function that will describe the scattering intensity in all of these regions for us. So that's the next thing that we want to do. Okay, so this is where we're going to have to put on our math pants again. And I'm going to skip the parts that aren't so important because, again, this is not a scattering class. This is a polymer physics and engineering class. So it's not important that we go through all of these things in detail, but what is important is that you see where these things come from, what the functional form is, and then what they do. So we'll start this way. P of Q, we'll start with a different color. P of Q is 1 over N times S of Q. And S of Q has been defined as 1 over N times that double sum. So this will be 1 over N squared, and then the summation j goes from 1 to n. Summation k goes from 1 to n. And then that function, that exponential function, the average value of the function exponential minus I q dot r j k, like that. I'll also say as we're looking at this, I is going to be the normal square root of minus 1. So it doesn't matter what field you end up in, there's always going to be complex numbers. So get comfortable with them. We're going to see them again and again and again. So if you look at this, P of Q is going to tell us how our scattering decays as a function of Q. And it just depends on this function. So our goal is really to figure out what is that function. And if we can do that, then that's that. We've solved the problem. So how are we going to get it? Well, the problem is that there is no one value of RJK, right? RJK occurs with a probability P of n and r jk, which we've seen before. So how do I get the average of the function? Well, every value of rjk that can exist, that has a non-zero probability, is going to contribute in some form to this function. So I need to take all of these things into account. In other words, I need to actually calculate what the average value of that function is. And so I know how to do that. The average value of this function is just going to be the integral of that function with the appropriate probability function integrated over all possible values of rjk. So what does that look like? That looks like the integral as rjk goes from actually minus infinity to infinity of the function. That's what I want the average value of. If you've taken quantum mechanics, it's kind of like expectation value. Okay, it's the average value that will show up. This will be the function exponential minus I q dot r j k, and then multiplied by the probability that I'm going to have that rjk to begin with. So this will be multiplied by the probability. Just put it in as we did before, rjk. And then we have to integrate over all possible values of rjk, and that's why it goes from minus infinity to infinity. So this, again, this function here is a Gaussian. If nu is equal to 1/2. If nu is not equal to 1/2, we will assume that it's a Gaussian. E to the iq dot r times that probability distribution. I want you to stop for a minute, think back. You must have had this at some point. Probably differential equations. This is by definition a Fourier transform. So this is the Fourier transform of the probability of n rjk. Okay, so we're moving from something that's given in terms of rjk to something that's going to be given in terms of q. So you can look this up, or you can do it. I'm not going to do it here. Again, we're going to skip some of these details. But you could look up what the Fourier transform of a Gaussian is, and you'll find that the Fourier transform of a Gaussian is a Gaussian. So if you have a really fat, wide Gaussian, then the Fourier transform will give you a sharp Gaussian, and vice versa. So the result of this is that the average value of this function will be the exponential of minus q squared, the average value of rjk squared, divided by 6. Okay, so now we can use that. Now we have this function, and we can substitute that function in for that one, and it's a little bit easier to work with because we're not looking at the average value of that exponential function. We're looking at the average value of rjk in that exponential, and we got rid of the minus 1. square root of minus 1. We got rid of I, right? Okay, so if we substitute that in, then we'll get that P of Q will be 1 over n squared. Summation j goes from 1 to n. Summation k goes from 1 to n of the exponential of minus q squared times something over 6. Okay, here's where self-similarity comes into effect. What is RJK on average? What is the average value? What's the expected value for RJK squared? Well, this comes from the chain statistics. This is why we did this. RJK squared is going to be Kuhn length squared times the number of monomers between them to some power. So this is, in other words, J minus K, that's the number of monomers between J and K, to the 2 new power. And we can substitute that directly in. So this becomes, I'll write it in a different color so that you can see it, times B squared J minus K to the 2 new power. And there we have it. Okay? So what's next? Well, I'm just going to go through, we're going to evaluate this expression. We're going to arrive at the form factor, and we're going to look at the scaling of the form factor to make sure it makes sense, and then we're done. So to do this, you can work with summations. You can play tricks to look at what the closed form solution of a particular sum is, and that's how some people do it. I prefer to do it this way. Let's take the continuous limit. So we'll move from the sum as j goes from 1 to n and replace it with an integral from 0 to n of du. And we'll do the same thing with k. So the summation as k goes from 1 to n, we will change over to an integral 0 to n dw. So what we're doing is we're moving to a continuous limit. Okay? Much easier because you and I work with integrals all the time. We don't necessarily work with coming up with closed form solutions to sums. So let's do that. We'll just replace these sums and we'll get that P of Q is equal to 1 over n squared, integral from 0 to n of du, integral from 0 to n dw. And now let's put in our exponential function. And so this is going to be the integral of the exponential minus q squared b squared, u minus w to the 2 new power over 6, and close the brace. So this is the form factor for a polymer. So all we have to do is solve it. There's a couple problems. This doesn't look like the most fun thing to solve. Why? Well, one reason it doesn't look so fun is that we've got absolute value, because the number of monomers between J and K, or in this case U and W, should always be positive. So we have to put the absolute value in there. So we can get around this a little bit. So we can get around this. In some years I've shown this, in other years I skip it. I've skipped it this year. You can take the expression for the radius of gyration and manipulate the sums a little bit and simplify it. And you can also show that this form factor is the same thing as 2 divided by n squared, integral from 0 to n of du, and then the integral from u to n dw. In other words, you don't double count. You only count one pair of distances, one pair of j and k. You only count them once, and so that gives you the factor of 2 in the numerator. And so then you're going to get, in this case, the exponential of minus q squared, b squared. W will always be greater than or equal to u. So this will be w minus u to the 2 nu divided by 6. Okay. So we're going to solve this integral to get the angular dependence of our scattering. First thing we're going to do is we're going to split up this n squared and take it inside, and we'll divide u by n and w by n. That's the first thing we'll do. Second thing we'll do is we'll define u. Let's not call it u. It's too many u's. We'll call it, let's call it capital H for whore. We'll call h, we'll define this as being q squared, b squared, capital N, the degree of polymerization of my chain, divided by 6. And if you look, that's the definition of Rg squared. So this is the same thing as q squared, Rg squared. Okay, so this is going to simplify this a little bit. We'll have that the form factor is equal to 2. Integral from 0 to n of du prime, just because it's now been divided by n. Oops. Speaking of that, if u is equal to n, then u prime, which is u divided by n, will be 1, not n. Second integral will go from u prime to 1 of dw prime. And now let's work with the exponential a little bit. This exponential will become the exponential of minus u, no, I didn't call it u, minus h times w minus u to the 2 nu power. But it's not quite that because I've got an n absorbed in h, so I have to divide this by n like that. Okay, so you can see what's going to happen. Sorry, technically this is n to the 2 nu. So this is technically n to the 2 nu here. So I can divide through. I can divide w by n. I can divide u by n. So what we'll do is we'll let nu equal 1/2. And then what our form factor will become is something much simpler that we can solve for. So 0 to 1 du prime, u prime to 1 dw prime, exponential minus h, w prime minus u prime, and that's it. Okay, so we're going to first solve the case where nu is equal to 1/2, and then we'll talk about what happens if u is not 1/2. So this is doable, right? This is not such a bad integral. We'll just integrate with respect to w first, put in our results, see what we get, and then we'll integrate with respect to u prime. Okay, let me get my notes so I don't make a mistake while we do this. Okay, so the first integral, the integral over w prime, will give us, let's see, 2. We still have this integral left, 0 to 1 du prime. And then that integral, that first integral of the exponential, will give us minus 1 over h times the exponential of minus h times 1 minus u prime. And then minus 1. Well, let me just put it. I'm a little bit flustered here because this is the second time I'm doing this today. I recorded this the first time, and then after I was done at 1 hour and 3 minutes, I found out that the software didn't record the iPad. So now I'm doing this for a second time in a row. So my brain is pretty exhausted right now. Anyway, this exponential will be 1. So what do we get? We'll carry the minus sign inside there. So we'll get that this is equal to 2 integral from 0 to 1 of du prime over h times 1 minus the exponential minus h times 1 minus u prime. All right, so that's pretty easy to do. We'll just do it in 2 steps. So we get, for the first term, that's the first term, we get 2 u prime over h evaluated from 0 to 1. And then the second integral is minus 2 integral from 0 to 1 of du prime over h times the exponential of minus h times 1 minus u prime. Almost there. So this 2 over h and then minus 2. This exponential is a little problematic, so we'll take this term outside since it doesn't depend on u. And then we're just left with the second term. So this is term 1 and term 2. So this will be 2 times the exponential of minus h divided by h, and then integral from 0 to 1 of the exponential of plus h u prime du prime. So far, so good. All right, so this integral is easy. Integral of exponential is easy. So this still is 2 over h minus 2 exponential of minus h. We get another h from the integration, so we get h squared in the denominator. And then we have exponential of h u prime evaluated from 0 to 1. All right, a couple more lines. So 2 over h minus 2 exponential minus h squared, exponential of, or the exponential of h u prime when u prime is equal to 1 will give me exponential of h. When u prime is equal to 0, this exponential will be the exponential of 0, which will give me 1. All right, so we've got h squared down there, h here. So that's going to give us a way to get a common denominator and combine these things. When I multiply e to the minus h times e to the plus h, this will give me 1. And so I'm only going to have the e to the minus h come through here. So I'm going to group these things together, common denominator, all this stuff. And I'm going to substitute in, remember h is q squared rg squared. So I'm going to substitute that in as well. And what I end up with is the final result. The form factor is 2 divided by q squared rg squared squared, and then multiplied by q squared rg squared plus the exponential of minus q squared rg squared minus 1. And so the reason I went through so much detail is this is a hugely important function. This is the most important thing that you could know as polymer scientists when it comes to, let me undo this, when it comes to interpreting your scattering measurements. So I got too close to the edge. Okay. I was trying to circle it. I'm not going to circle it. So this is the Debye function. Uh, 1915, I believe. That's when this is from. So this is the angular dependence. So in terms of our scattering function, I of q, we get a constant value out here for q less than Cn divided by n to the 1/3. And then after that, our Debye function takes over. And we get that term. So this is related to P of Q, just with some prefactors in front of it. Okay, so I'm going to show you in the next video how this works with some real neutron data and show you how well it describes the functions. But there's one last thing that we need to do in this video, and that is this region we understand really well. We derive this function for P of Q. Does it give us the appropriate slope in here? Does it agree with Perot's law? So let's do that part. That part is pretty easy. That's pretty straightforward. So the limiting behavior, we'll check out the limit. What is the limit? As Q goes to infinity of P of Q. Well, let's leave the prefactors alone. So we've got 2 over Q squared RG squared squared. Then inside here, we've got Q squared RG squared minus 1. And then we have that exponential term, e to the minus Q squared RG squared. Well, if Q goes to infinity, that function goes to e to the minus infinity. E to the minus infinity is 0, so we get 0 for that term. And you can see that this term is approximately Q squared RG squared. And so we get some cancellation, and so you see that P of Q goes like 1 over Q squared RG squared, or Q does indeed scale as Q to the minus 2 power. So it does work. It gives us the appropriate limit. Fantastic. What if that's not equal to 1/2? Well, then this function doesn't work. And it's no surprise that it doesn't work. We derived it for nu equals 1/2, so why should it work in the other cases? In that case, you'll find that the intensity, of course, decays as Q to the minus D, which is going to be the same thing as Q to the minus 1 over nu. So this function is not going to have the right decay behavior. And if you go up and you take this approach with the integrals and you try to derive a form factor, if nu is not equal to 1/2, you can't do it. You can't do it analytically. So you can do it in terms of these other functions called lower incomplete gamma functions. There'll be functions of 1 over nu and this thing we called h. I'm not going to do that though. If you're interested, there will be a PDF of the paper my student and I just wrote in the file section on Canvas. You can go through, it's in the appendix, you can see how it's derived. I'm not going to do it here. It's, again, a little bit outside of the scope of what we're talking about. That's more for our scattering course, but the Debye function is so important that I really wanted to cover it here. And I'll also be honest with you, I mean, it's useful to see where these come from, at least once, to see how to derive these. But for most of the systems you look at, these functions are already going to exist in the software. So you have to be able to identify what the appropriate function is to fit your data with, but you don't have to do the derivations. In fact, it's people like me and many others who do the derivations as part of our research and release the software as open source software usually, so that people in the community can use it to fit it, so that you don't have to do the derivations and the really detailed analysis of it. So this is good enough for our purposes. If you're trying to fit a polymer, this will usually always work, regardless of the value of the Flory exponent, but it's not entirely correct. This Debye function is really only correct if you have that if you have no excluded volume, if your Flory parameter, your Flory exponent is equal to 1/2. So I'll show you a little bit in a hands-on way what that looks like in the software, and you can see what the differences are, kind of, sort of. But I'm going to end the video here until next time when we actually look at how SASView works.